Psychonomic Society. I'm Stephen Lewandowski from the University of Bristol, and I'm the chair of the Psychonomic Society's Communication Committee. And it is in that role that I'm here today to introduce the series and our speaker. Let me give you a brief background to how this came about, because we need to acknowledge the pioneering efforts by the University of Mannheim in Germany, who launched this One World Cognitive Psychology seminar in early 2020 to continue to provide a platform for dissemination of research findings during the COVID-19 pandemic. And so we are very grateful to the Mannheim team, Beatrice Kuhlmann, who's here today, Micah Kroneisen, Art Broder, and Edgar Ehrenfelder, who put on this series for about a year with weekly talks on Zoom. Now, the Psychonomic Society has taken over this series, has adopted it, and it is our intention to make this a standard feature of our activities from here on. So thank you all for joining us. It's fantastic to have more than 200 of you here for this inaugural lecture. And just in terms of housekeeping, very briefly, please use the Q&A facility for questions rather than the chat. Beatrice will be monitoring that, and she will be handling the discussion at the end. One advantage of the Q&A facility is that you can vote on other people's questions, which makes it easier for the moderator to identify popular topics of discussion. So, and having said all that, it is now my great pleasure to introduce our inaugural speaker, Jeremy Wolfe. He doesn't need much of an introduction, but I'll give you one anyway. He's a professor at Harvard Medical School. He received his bachelor's degree from Princeton and his PhD in psychology from MIT. Now, he's held all sorts of very prestigious posts, including president or chair of the Federation of Associations in Behavioral and Brain Sciences, and indeed the Psychonomic Society. And he's done a lot of work for the Society, including being the founding editor-in-chief of our latest journal called CREEPY, which stands for Cognitive Research Principles and Implications. And he was elected to the American Academy of Arts and Sciences in 2019, and he's now here to talk to us about, if you don't find it often, you often don't find it, effects of target prevalence and visual search in decision-making. Over to you, Jeremy. Thanks so much for doing this.
Thank you, Stephen. Nice to be here, though here is a sort of an odd term in this particular, well, I know where I am. I'm in my home near Boston, Massachusetts, and it's interesting to see the spread of people around the world. One of the few advantages of the COVID era is that we can now be together all over the place all the time. Beatrice and or Stephen, I do hope that you will stay on camera, because it's so much nicer to be able to talk to somebody. I'm apparently talking to a bunch of people, but they're all out there in the magic ether somewhere. So let me start with a couple of disclosures. My funding is largely US government funding, though I say I don't have it here, but I have had some funding from General Electric and from Google. The work that I'm going to talk about is very much the work of many other people over many years. I will try to highlight them as we go along here. I just get to be the spokesperson for this work. Well, let's start talking about visual search. So the world is full of search tasks, from Where's Waldo to picking alligators out of the Lego bin in your children's toy room. And these search tasks fail with some regularity. Here you're supposed to find an animal, which you might or might not find, but once you get your attention onto Mr. Parrot here, it's easy enough. The parrot is in some sense right in front of your eyes, but somehow you may or may not have failed in that particular search. Experts fail in important search tasks. This is an example from a search task I will come back to later, where radiologists are looking through the lungs for these round white lung nodules that are a sign of lung cancer. And in our experiment, they happened to miss this gorilla that we had inserted into the image. You're not radiologists, so let's point this out. Let's see if we can demonstrate this for your purposes. So as I say, lung nodules are these sort of white spherical things in the lung. So look for golf balls, which we'll do as a reasonable stand-in here. So you're searching for golf balls in this image. And I am guessing you found that one. And I'm pretty sure you found that one, even though it's a little atypical. Stephen, did you find those 5? No, how about that one? So they're perfectly visible. In fact, that one that's up there above the little Greek temple is much more salient than the ones that you did find. But you looked at that scene and you somehow failed to find the target that I asked you to find. If we go back to these expert tasks, some of these expert tasks are much more important than looking for many of these expert tasks are much more important than looking for golf balls on mini golf courses. You've got here a couple of scan pads from radiologists looking at mammograms. There are experts looking at overhead imagery to figure out where there are missile bases in North Korea. There are experts looking at your carry-on luggage, looking for guns, bombs, and knives. One of the interesting characteristics of these, of many of these expert search tasks is that they're low prevalence tasks. That is, the thing that you are looking for is rare. If you're doing screening mammography in a North American population, cancer shows up in about 3 in 1,000 women being screened. At the airport, of course, the rate of actual threats in luggage, is, not counting your water bottle, is very low. It'll be a lot of territory that you're looking over before you're going to find that missile base, and so on. And so what I want to do today is explore the connection between prevalence, the prevalence of targets, and these looked but failed to see errors. Prevalence isn't by any means the whole explanation for why we miss things, but it's a piece of the puzzle. And that's what I want to introduce you to today. So I'll tell you how low prevalence becomes a source of errors in visual search. We'll talk a little bit about how to model this, what prevalence tells you about both visual search and about perceptual decisions more generally. And then we'll talk about how prevalence modulates errors and can contribute to failing to see what's right in front of your eyes. So let's start with prevalence in baggage screening. This is sadly appropriate 20 years after 9/11. That's when there was a lot of increased interest in things like baggage screening. And that's roughly when we started getting interested in this topic. As I say, there aren't a lot of threats in real bags at the airport. Does this matter? Here's a quick look at what that task looks like. It's dual energy X-ray. Blue means metal. Orange means organic. Green is somewhere in between. roughly speaking, people are looking for, well, they're looking for threats, guns, bombs, and knives. When we do this in the lab, we only did guns and knives because bombs are too difficult for non-experts. So if we were together, I would get you to raise your hand or something when you actually find a threat. It's a difficult task. If you were looking for a bomb, by the way, you're looking for an orange thing that's a bunch of organic material and some metal that would be serving as a detonator that was interacting with that orange thing in a way that was disturbing to you. As I say, it's a very difficult task. A peanut butter sandwich packed in with your electronics would look quite a lot like a bomb, in fact. And so it's a difficult task. This is about as easy as it gets. That's a knife with its blade conveniently out for you. So does prevalence matter? Does the fact that you're looking for something rare matter? Todd Horowitz and I did an experiment on this some years ago, where one way to think about it is, let's take 20 bags that have guns and knives in them, and we'll either mix them in with 20 other bags, so 40 bags, where the prevalence is 50-50, or we'll mix them in with 1,000 bags, so the prevalence goes down to 2%. Same threats in both cases. What I'm showing you here is the error rate, misses and false alarms on the x-axis, error rate on the y-axis. See my nice orange note. I am not showing you the data from airport screeners at this point. If I was, I could not show you the actual error rates because that would be so-called security sensitive information. These are data from naive volunteers. And what you can see is that the same errors are missed twice as often, roughly, when they're rare as when they're common. If you look at the false alarms, you see that those go the other direction. But if you ask yourself which kind of error you want to minimize at the airport checkpoint, you'll understand that doubling your miss errors is not a good thing. All right, found this in the lab. Would it ever really happen in a real world setting? Well, let's switch to radiology, where, as I said, cancer in screening radiology, screening mammography is quite rare. We did this experiment. We, in this case, is spearheaded by Carla Evans, now at York in the UK. We did an experiment where we took 100 cases that we knew, where we knew the ground truth, 50 with cancer, 50 without cancer, and we either showed those to radiologists all in one block, so 50% prevalence, or we slid them into clinical practice very slowly over months. So we didn't change the very low prevalence in the clinic very much. And in the clinic, they thought they're doing their regular work. We just happened to put in some fake control cases where we knew the right answer. And this should look familiar. This is basically the same pattern of results that we got in the lab with naive subjects. Same cancers. If you look at the miss errors, twice as many of them were missed in the clinic when the radiologists thought they were looking for real disease, as compared to in the lab when they were doing us a favor looking at a bunch of images. Again, the false alarms are a little lower in the at low prevalence, but again, it's the miss errors that are really potentially catastrophic here. Here, by the way, is the version with transportation security officers, the screeners at the airport. If you look at this y-axis, you'll realize you cannot figure out what that error rate is, but you can tell that something different is going on between high and low prevalence. And I'll tell you that at the airport checkpoint, the story is very much the same as it is in the radiology clinic or in the lab. So why does low prevalence make you less likely to find a threat? One idea, which many of you who are experimentalists can probably sympathize with, is it could just be a motor error. At low prevalence, you're just going, boom, no, 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 and then a target comes by and you hit no again by mistake. This was actually an idea proposed after we had our result come out. Fleck and Steve Mitroff proposed this, and you can see in their data here, all those red arrows are pointing to a big decrease in errors in their experiment when they allowed their subjects to correct the response. We went and did a similar kind of experiment. We basically redid our experiment, allowing our observers to correct the response if they wanted to. So what you see, the green arrow on the figure here is showing you the standard prevalence effect before, in their first response. And then we said, basically, are you sure you want to change your mind? And basically, people didn't want to change their mind. People do make motor errors, but it's not the explanation for the prevalence effect in general. All right, so why do you make those errors? The core, very important piece of the answer is that you become more conservative. Obviously, I don't mean this in a political sense. I mean this in a signal detection sense. If let's stick with the baggage example, you're looking for the prevalence of a threat, and your stimulus is on some sort of scale running from no threat to threat. The bags with a threat in them, the signals come from one distribution, the ones with no threats come from a noise distribution. The separation between those two distributions will tell you how well you do that task. That'll be measured by something like D prime. What we're interested in here is the criteria. You can only, if you got to say yes or no, you've got to put some sort of a criterion on that, on top of those two distributions. And if you get a signal that's to the right on this graph of that, you're going to decide there's enough signal there that you'll say, yes, there's a threat. And if it's to the left, you'll say no. Now, if you don't want to make, so that this will determine then the mix of errors. If you say no when there is a threat, that's a miss. And if you say yes when there isn't a threat, that's going to be a false alarm. You can change the balance of errors that you make by sliding the criterion from left to right. Conveniently enough, the nomenclature of liberal and conservative fits our standard both political world and graphics world in signal detection. So if you want a rule of thumb, a conservative criterion shift is indeed a shift to the right in the standard way of making these pictures. And that's what happens when items are, when targets are very rare. If you think about it, if targets are very rare, most of the errors that you're going to make are going to be false positive errors. They're going to be false alarms because most of the items have no target. If you make a mistake, it's going to be a false positive. And you might think to yourself, oh my goodness, I'm making a lot of false positive errors. I'd better become more conservative about saying yes. And that's in fact what you do. We can see this more clearly, or perhaps nice and clearly, on a standard receiver operating characteristic curve. That's where you plot false alarms on the x-axis, the hit rate, or 1 minus the miss rate on the y-axis, and your performance for any given level of your ability to do the task. If you were perfect, you'd be up in the upper left-hand corner. If you're a chance, you'd be on the main diagonal here. And your performance forms a curve, an ROC curve in that space. And what we've got on this graph is showing you what happens when you vary the prevalence. Basically, you slide around on this ROC curve. When you are at low prevalence, you adopt a conservative criterion where you make fewer hits and fewer false alarms. You say yes less often, so more miss errors. If you go the other direction and you have a high prevalence, very high prevalence situation, you get the mirror effect. You say yes all the time, and as a result, you find all the targets and you false alarm at a very high rate. And if the prevalence is sort of a standard lab 50-50, you're at a more neutral criterion typically. So big piece of these prevalence effects is this criterion shift, but that's not the whole story, especially not in visual search tasks. Here we can show what's going on. Here's another part of the story. Here what you're seeing from a visual search experiment is the reaction time. Oh, the y-axis isn't labeled. That should be milliseconds. And what you can see is that the time to say yes, those are the hits, is much faster in this particular experiment than the time it takes you to say no, either if it's a miss or a true negative, same amount of time for those roughly. And this is at 50% prevalence. Look what happens when we take the same stimuli and operate at low prevalence. What you can see is that the no responses, the true negatives and the misses become much, much faster. That's the hallmark of a speed accuracy trade-off. I'm putting a picture of Ray Klein here, not because he and I did this work, but because he reminded me quite a lot about the existence of speed accuracy trade-offs, and I'm just proving that we were paying attention. If you start saying no much more quickly, in a visual search task in particular, you're going to end up saying no before you had time to find the target, and you're going to end up missing more targets. So we can expand this story of prevalence to have these two components in them. Here's an example. These stimuli are taken from another clinical setting. Here we have pathologists looking for evidence of cervical cancer, which involves these slides full of thousands of cells, and you have to see if any of the cells look disturbing. So you'll attend to a cell, decide that it doesn't look disturbing, let's say, move to another cell, select again, and so on. But how do you decide when it's time to quit? At some point, you're going to have to get out of the search. A line of research that I won't talk about strongly shows that you don't do this by sort of mentally marking every item that you attended to and crossing it off. That's just not possible. What you seem to do is you've got a quitting threshold in your mind, and you can think of this as a diffusion process of some sort. A signal is accumulating towards that quitting threshold. There are various things that you could imagine that that you might be accumulating. Could be time, could be number of attentional deployments, number of items rejected, so on. They produce similar kinds of results in this kind of modeling. And you keep going. If you find a target, you end the target with a yes response. But if you don't find a target, at some point that quitting threshold will be reached by that diffusion process, and you'll quit typically with a no response at that point. You'll respond no. So we can think of the prevalence effect as involving two different thresholds, really, showing up at two different parts of the search process. There's an effect at the level of specific decisions. That's this internal criterion shift as you become more conservative at low prevalence. And there's what boils down to a speed accuracy trade-off. As you say no, no, no successfully more often, you drop that quitting threshold. And that in turn causes you to miss more items. We can see that if we do, here's an experiment that kind of illustrates it. What we did was we ran people for 1,000 trials on a search task but we slowly, over the course of the 1,000 trials, we varied prevalence, starting very high, dropping to very low, and then rising back sinusoidally to very high prevalence. And if you look at the error rates in this experiment, you can see the false alarms and misses trading off against each other. The red lines are the misses. You can see that they're high when the prevalence is low in the middle of this experiment. The false alarms are in blue, and you can see them rising as the prevalence rises. And basically what you're seeing here is the manifestation of that criterion shift. If you look now at the reaction time, what you can see in green is that the amount of time to find a target doesn't really change with prevalence. But the amount of time to say no changes dramatically with prevalence. It gets faster as prevalence gets lower and slower as prevalence gets higher. You can also see that that red line of the reaction time is shifted to the right of the actual prevalence. That gives you some feeling for what's defining prevalence for the observer. How much of the prior history are you looking at? And it turns out that in these experiments, a couple of dozen trials was what you were using to estimate the current prevalence of the targets. You're not doing this by counting them explicitly. This is all happening quite implicitly. Indeed, as a subject in this, one of the interesting aspects of these prevalence effects is how cognitively impenetrable they are. Even though I might have programmed the experiment and know exactly what's going on, my miserror rates still go up at low prevalence. The chunk of my brain that's doing this doesn't care that much what I'm thinking about it. If you want more detail about this and some code that will let you play around with it and simulate it, by all means, check out the latest version of the guided search model, which was just published in a fine Psychonomic Society journal, I should add, a couple of months ago. Okay, so low prevalence makes you less likely to find a target. What are we going to do about it? How are we going to cure it? I've been working on this for some years, mostly by promising various government agencies that I was going to cure it. You may guess by the fact that we've been working on it for a long time that we did not come up with a magic bullet cure, but we did learn a bunch. We thought, for instance, there's this speed accuracy trade-off. Why don't we just slow people down? So we imposed speed limits on our observers, and it just didn't work. We made the reaction times a second longer and failed to change the error rates. I don't know what they did with the extra time, but they didn't use it to cure their prevalence effect. A number of people have tried what in the radiology literature would be called double reading. If you've got if you've got people making mistakes, let's get two people to look at the stimuli. That should help, and indeed it does. It doesn't help quite as much as probability summation would tell you, because the errors are not independent of each other. And from a practical point of view, the difficulty is that you now need twice as many observers. That can be worth it to you. So Molina and company at Warwick in the UK are in a country where mammograms are double read. All mammograms are looked at by two experts, and that does bring down the miserror rate. The US has not adopted that, and the main reason for that is the need for twice as many readers or twice as much reading time. One idea that has been suggested a number of times is, let's lie to people. If people miss fewer items when items are common, let's just tell them they're common. And indeed, that does make a difference. That does have an impact. But it runs into a problem that we've seen in a somewhat different context when we apply computer-aided detection systems in radiology. CAD systems are not lying to you, but the similarity is that what a CAD system is doing is it's putting a mark on the image, at least in one of the main uses of CAD, it's putting a mark on the image and saying, hey, I think this is cancer. Now the difficulty, and it's a low prevalence problem with CAD, is that because it's low prevalence, unless the system is essentially perfect, most of those marks are actually false positives. In effect, the CAD system is trying to is sort of saying to you that the prevalence is much higher than it really is. The difficulty with this is that people don't like being lied to. In CAD, they figure out that most of these marks are systematically wrong, and they come to systematically disregard them. And this is probably the case if you give false feedback in any real situation out in the world, right? If you start telling people at the checkpoint, oh, you just missed a gun, but you didn't miss a gun. The guy at the checkpoint's going to figure that out because there should be a lot of excitement if there's a gun in the bag. And once the observer, the expert, learns that you're lying, the observer is simply going to stop listening to you. So it works under laboratory situations, but it's not probably a general solution to the problem. Here's a recent clever idea in press at Psych Science. Here's the idea: you're looking for a good T among broken T's and L's. And that red arrow is showing you a perfectly lovely standard issue prevalence effect. At low prevalence, you make many more miss errors. So what Taylor and company said was, let's tell the people that what they need to do is to mark the most T-like item on every trial. And then what you discover is, lo and behold, the miss errors go way, way down. Which is good, and you can sort of figure out what's going on here. If you say you've got to mark a target on every trial, you're in effect saying to them, you need a really, really, really liberal criterion. So you're moving your criterion way over to the left, and now you don't miss things. Clever idea. There's if you think about what you now do with this in the real world, there's an issue. If you've marked something on every trial, now you still need to make a decision about that item. So you have made it more likely that you're actually going to find the target. You're going to pick something in this bag. You're going to pick something in this mammogram. But now you have to decide whether what you picked is actually a threat, actually a cancer, or is just the most suspicious looking thing. This is, in fact, more or less what is done in a number of medical settings. If we go back to this cervical cancer screening, the way that cervical cancer screening works, at least at my hospital and many other US hospitals, is you have technicians, trained technicians, but not pathologists, reading the images initially. They are instructed to read with an extremely liberal criterion and to send on to the clinician anything that looks vaguely suspicious. So basically what the clinician is doing, what the technician is doing is getting rid of the ones that really, really don't have anything in them. But anything that might look a little suspicious, send it to the clinician. So that's in fact a sort of a double reading version of this Taylor et al. Idea of marking the most suspicious thing in the image. The bottom line remains, however, that as we said in a paper some time ago, that prevalence is a stubborn source of error. It's very difficult to actually get the prevalence effect to go away. There are ways, and what we're looking for really is ways to manage it. So let's go back to this idea of, in a sense, marking the suspicious object and now making a decision. That now asks us to make takes it out of the world of search and just says, let's look at the effect of low prevalence on decision by itself. And we know that there are prevalence effects that aren't specifically visual search effects, going back to the vigilance literature many years ago, for example, and lots of examples can be brought forth for prevalence effects that are not specifically visual search effects. A new interesting wrinkle on this came up a couple of years ago when David Levari at Harvard did what seems like a very simple experiment. He asked subjects to say whether a dot was blue or not. So you look at that one, yeah, that looks blue. How about that one? I don't know, it looks kind of purple to me. Steven says it looks purple to him. How about this one? Yeah, he's looking back and forth, he's not sure. And that's what the data would look like, right? So here what we're doing is we're plotting a psychometric function. We're going to vary the color on the x-axis. We're going to vary the proportion of blue responses on the y-axis. If it's purple, you're going to say it's not blue. If it's blue, you're going to say it's blue, and there'll be a function in between where it's ambiguous. These might be the data if you are sampling randomly from across this continuum. What's going to happen if you make the blue dots rare? So let's take all the dots to the right of the middle of this continuum, and we'll make examples from the blue end of this continuum very rare. What's going to happen? Well, the low prevalence effect, the standard low prevalence effect, is going to say what's going to happen is you're going to miss more. You're going to, something that was ambiguous, you're going to declare is not blue. What made Levari's paper interesting is his data went convincingly in the opposite direction. When the low prevalence items, when the blue became less prevalent, you actually ended up saying that more things were blue on this continuum. He called this prevalence-induced concept change, PIC for short. So here's a mystery. Everything I've told you so far says at low prevalence, what tends to happen is that ambiguous stimuli become less likely to be labeled as targets. And here you've got the result going in the opposite direction. What's going on? We have a brand new paper where Wanli Yu and a bunch of others, including David Levari, and I tried to figure out what was going on. And one interesting piece, the critical variable that we identified in this paper, is feedback. If you give feedback after each trial, you say, yeah, that was blue, no, that wasn't blue, and so on, you get a standard low prevalence effect. That's what you can see on the right-hand side. If you don't give feedback, you get this, this PIC effect going the other direction. Now, oh, and we've replicated this. It's not just color, and pretty much any continuum will do. We think here's the results for items that range from smooth to spiky, or from booba to kiki. And what you discover is that with feedback, you get a standard low prevalence effect. Without feedback, with these stimuli, you get a somewhat anemic PIC effect going in the other direction. What's going on here? One way to think about this, if we go back to that signal detection representation, is that at low prevalence, what you've done is you've made that signal distribution much smaller. There are many fewer items in there. And if you imagine, for instance, that what you're trying to do is to balance the number of times you hear that you missed a target with the number of times you hear you false alarmed. Then at low prevalence, you're going to shift your criterion to the right because you've been making so many false alarms. You're going to have to move the criterion to the right to cut down the number of false alarms. But suppose you're not getting any feedback. When you're not getting any feedback, the only thing you can monitor in these sort of laboratory experiments is the responses that you're making. At 50% prevalence, you're going to be saying blue, not blue, not blue, blue, about half the time. Now the prevalence drops very low and you're saying not blue, not blue, not blue, not blue. You think to yourself, oh my goodness, I'm not saying blue enough. And that will shift your criterion in the opposite direction and produce a pick effect. Real world situations are complicated because in the real world, you tend to get partial feedback from things. If you think about the airport, if you're at the airport and you think you found a threat, that bag is going to need to be opened and you're going to learn whether or not that was really a bomb or just another peanut butter sandwich or something of that sort. But you're not going to get any feedback from the situation. You're not going to get any feedback about your miss errors typically, at least not until something catastrophic happens. Similarly, in a medical setting, you tend not to get information about the cancer you missed until years later when you get sued for malpractice. That's not the whole story about this decision component in prevalence. It's very much a story that's still developing. But in the bit of time left, I want to get back to this question of missing clearly visible targets. That gorilla experiment that I mentioned at the beginning was done with Trafton Drew and also with Melissa Vo. Trafton's now at the University of Utah. And so we stuck this gorilla in the lung and 20 of our 24 radiologists missed it. Now, it's important to mention that this wasn't because we had lousy radiologists. It was because inattentional blindness is a thing, and you don't become immune to that thing just because you've become an expert radiologist. But why in the world would we bother doing an experiment like this? We did an experiment like this because we're interested in the problem of missing what are called incidental findings in medicine. If you're a radiologist scanning the lungs for lung cancer, the task is tell me whether there's lung cancer, but you're also always expected to report out any other clinically significant finding. Big lawsuit at my hospital some years back for a radiology case where the question was, does this woman have pneumonia? The radiologist correctly answered, no, she didn't have pneumonia, but he missed the lung cancer that she did have. Among, at least in US medicine, that's not only an unfortunate error, that puts you at a very significant legal risk. So these incidental findings are something you want to find, and there's something that get missed at a rate higher than we would like. So our argument in the paper was, oh, look, here's part of the explanation for why radiologists are missing incidental findings. This paper got a fair amount of notice in, among other places, radiology social media, which I didn't particularly know existed before this paper, but it does. The radiology, if you read down into the comments section, there was one line of argument where radiologists were saying, I would not have missed that gorilla. I don't actually believe those radiologists, but a more interesting complaint was something like this. The radiologists said, look, it's cute that they were missing this gorilla, but really gorillas just don't happen in the lung. And when I'm looking for incidental findings in the lung, what I'm looking for is things that I've been trained to find. So, I may be looking for lung nodules, but I know that there's a possibility of a broken rib or a pneumonia. And those are things that show up in the lung and that I know what they look like. So if you want to convince us that there's anything interesting going on, what you need is a task where observers make lots of errors, even though they know what they're looking for. And the last bit of data I'll show you today is from a paradigm we call mixed hybrid search, which is designed to do exactly that. So visual search is typically search for one target or one type of target among distractors. Hybrid search is search for multiple target types among distractors. And this example from the lung is a good example of a hybrid search. The observer is looking for cancer and pneumonia and broken ribs, and the heart's on there too, so you better check whether it's enlarged. Anyway, it's a hybrid search. And the version that we did in the lab looks like this. We told our subjects, you're looking for 3 specific targets, and they might be, in this example, that drink, that shoe, the table. And we also want you to look for any animal, any fruit, or any game, any toy. So a categorical target. Now, this is more like the situation in the clinic. You're looking for that specific nodule, but you're also looking for a more amorphous set of categorical, a more categorical set of stuff that shouldn't be happening in the lung. Here, we can try it as an example. So you got this in mind: drink, shoe, and table, any animal, any fruit, any game. You ready? Yeah, there we go. And you're all properly responding. Oh, yes, there's that drink. And now your quitting threshold has been reached, and you say, no, there's nothing there. And hopefully here, well, you should have found that boot, but with luck, you also picked up at least the animal and or the fruit, which are these categorical targets. In the real experiment, there wouldn't have been 3 different things in the same display, though we've done versions with multiple targets. I'm showing you data from either a specific target in the display or a categorical target or nothing. And here's the standard finding. In the experiment, in this experiment, for the data I'm showing you the error rates when categorical targets are just as likely as specific targets. And you can see, as ever, well, this is not a prevalence effect, but in this case, observers are missing many more categorical targets than they are specific targets. Now, it's important to understand here that this is not because these are items that are hard to detect. Our observers, in a control experiment, we went through and we had observers just identify the categorical or categorize the categorical objects, and they're all trivial. Nevertheless, people are missing them. Now, this is a situation where there's a target on half the trials, and of those targets, half of those targets are categorical and half of them are specific. Let's now mix this with the prevalence effect. If we cross this with the prevalence effect, what we're going to do is we're going to still have a target on 50% of the trials, but 80% of those 50% will be specific, and only 20% of the targets that are present will be categorical. And what happens when you cross this this mixed hybrid result with the prevalence effect is you get a really dramatic elevation of errors in the categorical condition. Now the chance that you're going to miss a target is 7 times greater for the categorical items than for the specific items. And again, let me stress that these are not ambiguous stimuli. These are not stimuli that are hidden in noise or anything of that sort. They're just sitting there right in front of your eyes. Oh, and they're not up there for a limited period of time. The stimulus is available until you push the button and make a response. So they're visible, they're there until you respond, they're clearly identifiable, and you're missing a third of them. And that's really what I want to leave you with here. So if we want to summarize this, if you think about it, the criterion shift in response to shifts in prevalence makes sense. If an item is extremely rare, you should be quite conservative about saying that it's actually present. That makes good sense out there in the real world. Having an adaptive quitting threshold makes good sense. I didn't stress the adaptive part of this. The idea here is that how do you set that threshold for when to quit? If you say nothing's there and nothing is there, well, you speed up a little bit on the next trial. And you speed up a little more on the next and on the next. If you make a mistake, you slow down. And if you look at sequences of reaction times, you can see that beautifully in lots of different data sets. And that adaptive kind of threshold setting is a sensible thing to do too. The difficulty arises when these sensible processes that have worked very well for us as animals for millions of years, presumably, when they meet these artificial tasks that are relatively unusual in the real world, where the prevalence is low, but where missing the target is deeply problematic. And in those cases, these processes that work really well under most normal circumstances break down, and you end up missing clearly visible things that are right in front of your eyes. I was speaking with lawyers yesterday who were consulting me about a law case that is going to be, exactly this talk, basically. I can't tell you the details. Maybe in a few years, I'll tell you the details. But let me tell you, this happens in the real world. People miss things that are clearly visible. There are multiple factors that are at play here, but prevalence is certainly one of them. So thank you to the Psychonomic Society for inviting me to do this. Thank you to the approximately 272 people who at least have their devices on. I see things in my peripheral vision happening in the Q&A, and I'll be happy to let Beatrice take over from here and see what's happening.
Thanks, Jeremy, for the really interesting presentation. There's lots of clapping hands in the regular chat. So you can imagine your applause. And we do have a few questions already. Keep in mind to use the Q&A box. It's right next to the chat for these. And you can also give a thumb up to a question that you'd be particularly interested in. And some have already started doing this. So we'll start with the currently most popular question, which is by Jeffrey Andre. Many of these studies involve many trials. What about a real world situation, like detecting and identifying a pedestrian? On a college campus, they are high prevalence, so we'll be less likely to miss them, right? On a limited access interstate highway, they are far less likely to be there, so we are less likely to see them. Is that logic correct?
I think the short answer there is yes, that that even these, obviously there's many trials involved here because low prevalence is a bit of a methodological disaster. You wouldn't do these experiments unless you had a rather specific reason for wanting to, because in order to get enough statistical power to see anything at 10% prevalence or 6% prevalence, you need a lot of trials. But there's no particular evidence that the result depends on having zillions of trials, and I think your analysis is indeed correct.
So we can miss the same target based on the context where it's less prevalent and more prevalent. Okay. The next question is by Kara Moore. To what extent does inattentional blindness explain low prevalence misses?
Well, so they're definitely related, and you in some sense it'll be a little dependent on how you decide you want to define inattentional blindness. It's important that to realize that the prevalence effect doesn't need to be based on the items being unusual in their own right. I mean, and that was in fact part of the complaint about our gorilla in the lung experiment, was that the thing that people were missing was a thing that was never going to be there. In the prevalence effect, you end up missing things that you perfectly well would have detected under other circumstances. Some of that is could probably be thought of as being directly analogous to inattentional blindness. Some of it is also early search termination, that people give up on the search under low prevalence conditions too soon. And I don't know if you'd want to call that, strictly speaking, inattentional blindness.
Okay, thanks. And then Mark Laurie wonders if the PICC results have something to do with the lack of inhibition too. In a visual search task, you have to ignore a lot of irrelevant stimuli. It also reminds me of oddball paradigm, where viewing similar stimuli one after another produces a P300 wave. Could the P3 be related to detection, and maybe having the irrelevant stimuli suppresses that response, producing an N200? Have there been any ERP studies on this?
Oh, are there any ERP studies on prevalence effects? Somebody on this call may want to pop in the answer that I'm failing to come up with out of my own memory. I can't think of an ERP study on this, and part of that, if there isn't one, the reason is because it's bad enough to do this in reaction time and error rate land. But if you think about ERPs where the data typically involve, let's average over a few gazillion trials. If you want to average over a few gazillion rare trials, that's not going to be a fun experiment. So one of the unanswered questions about this pick versus low prevalence distinction is just how much it does show up in search tasks as opposed to single item decision tasks, and that's an ongoing topic. And if somebody knows, if somebody is remembering that they did the ERP study that I am currently forgetting about, I apologize, and please pop it into the Q&A.
Okay. Nobody popped in on this yet, so. Next question by Nick Gasplin. Many of these search tasks shown in your talk seemed exceptionally difficult. The target was not very salient or easy to find. This may be a silly question, but does the prevalence effect depend on search difficulty?
So it's yes and. So it is the case that that the search difficulty makes a difference. But if you think about the last experiment, yeah, these, you know, with these kind of stimuli, we were getting a massive prevalence effect. And you wouldn't want to argue that it was difficult to decide whether this, what is he, a peccary or something, this animal is an animal. That you still end up making these sort of, you still end up seeing these prevalence effects with a fairly dramatic stimuli. If you have a very simple design where you're trying to do, I don't know, red among green, and you just have very rare red stimuli, that's the sort of situation where you really are going to get the kind of motor error version of the prevalence effect. You're not going to fail to see the red thing, but you might bang the button by mistake. But in an experiment like this one, you can miss an object that you would have no difficulty identifying as an animal. And the rate of missing it goes up substantially at low prevalence. So the difficulty of the task is relevant but not required.
Okay, thank you. Yeah, Nick also thanks you for the answer. And the next question is by Bethany Grounds. I know some research has found similar effects in visual comparison tasks, for example, face or fingerprint matching. But these are usually contingent on feedback. I was wondering your thoughts on the similarities, differences between these tasks, given similar effects are found in both.
Yes, these, particularly by the time you've moved out of the search domain into the single item kind of domain that we were doing with those Lavari style, what's the blue dot? What color is the blue dot? I think those are similar kinds of effects, and they are dependent. They do appear to be importantly dependent on feedback. So from a basic science vantage point, that helps you get at the mechanism. The feedback question gets you helps get at the mechanism. From the sort of use-inspired basic research line, which is the tagline for the journal that Stephen mentioned at the beginning, that's the stuff that Creepy is devoted to publishing. But from that, if you start thinking about the real world, the complication is that the nature of feedback is not always horribly clear. Real world tasks often generate some degree of feedback, not from the observer, but not from the experimenter, but from the observer, right? If you think about, are we still looking at the stimulus that's here? We could probably get rid of it. But if you're looking at that pig thing here, you know you're looking at an animal, and you're getting some sort of feedback from that, even if I'm not giving it to you. You end up in the real world getting sort of partial feedback in many situations, and it's a little difficult to understand. Well, more work would need to be done on how real world feedback impacts on these prevalence effects under circumstances that we might care about out there in the real world. The real world's a pain. You don't get to run thousands of trials of the same search or the same decision, and people know stuff, and you don't get to eliminate that knowledge in the real world in the way that you can in the lab setting.
Yeah. You unshared your screen. I'm not sure if was that intentional.
Yeah, I can reshare my screen if that would make anybody happy, but I thought unsharing it means that you can see Lewandowski better, and that's always important.
All right, we'll move on to the next question, which is by Friederike Schlaghecken. Would it make a difference if you slipped in a small but unspecified number, like 1 to 3, of deliberately placed targets? So if the participant knows about this, and if it's relevant to them to find at least those targets, would that keep their decision criterion more liberal? And there is a comment on this by Todd Horowitz.
Yeah, I saw Todd's answer. Yeah, Todd is saying this is exactly what happens at airport checkpoints, is that they put in guns and knives and so on, and as a quality control mechanism. So the answer is yes, but so it's certainly the case that if you put in, if you take your prevalence up to 50% again, that you'll change behavior back. If you think about that under real world circumstances, it becomes problematic because you can't, typically you can't have the downstream consequences of a real error. Sorry, of a real target in the real world. If you put targets in the airport situation, we can't tell you what the prevalence is of false targets. They do that. We can tell you that it's way under 50%, and it's that even at the airport you're still operating at a low prevalence, in a low prevalence kind of regime. If you crank it up to where everything is basically, oh yeah, thanks for finding that, but it's not a real target, that produces its own problems. And if you treat all those false ones as real targets, that would have, if you in the radiology clinic, if you put in a whole bunch of false targets and you're making the radiologist do all the follow-up that you would do if there was a real false target, you would get downstream sort of process consequences that you can't really tolerate. There are also tricky little sort of medico-legal problems. When we were doing our experiment on prevalence in the clinic, we were inserting these false cases into the regular line of work. And the first version of our experimental design, had it actually gone through, it turned out to be a felony, which is not good as experimental designs go. The difficulty was that everything is electronic in medical land now. If you've got a whole bunch of inserted false cases, those are being reported to the state. They're now elevating the state's estimate of like disease prevalence and things of that sort. And it's very bad. What was the original question here? There was an original question. Whether
it actually impacts the decision criterion. So whether it makes it more liberal to have them.
Yeah, so if false targets are useful in the lab, they're difficult to implement in the field is the short answer to that question.
So they do work, it's just a question whether you may use them, yeah. So we can stick with legal implication. There's a question by Tom Carr who says that in real world situations with legal implication, to him it seems the fact that this happens to everyone and it's part of being human is a weak defense. But the cognitive impenetrability that you talked about briefly might be a stronger one in his opinion. So he's wondering if you could talk a little bit more about that idea, that argument.
The legal side of this is tricky because a lot of this ends up when these things do end up in court, it ends up in court where you have somebody missing a target of some variety, and but by the time it gets into court, the lawyers are pointing at the target, right? How could you miss this thing? The cognitive impenetrability piece, I think I have a limited range of experience as a expert witness in these things. I think it would be a relatively hard task to, you have to explain to your lay jury, typically, or even your non-scientist judge, why that makes a difference. It's my feeling is that that the best way to try getting this across in the sort of legal domain are demos like my mini golf demo, where you can actually give people the experience of missing something that's clearly visible right in front of them. Now and we're now mixing up several different effects at the same time. This isn't just about prevalence, but in the legal setting, these malpractice cases end up being about how could you have missed this? Any idiot can see it, and explaining why that's not necessarily true turns out to be tricky.
Okay, and we have a question by Anders Cecil, whether there are targets that are more resistant to the prevalence effect. For instance, something that the observer considers as threatening. And the suggestion is maybe a spider. Yeah,
I don't know. I'm trying to think if anybody ever did a prevalence experiment crossed with spider threat. Though I would say that guns, bombs, and knives and airport luggage are arguably more of a threat than spiders, and though maybe not as scary to people, but we certainly see prevalence effects with highly significant stimuli of that sort. It is the case that prevalence effects are less common with easily discriminable stimuli, though we talked about that briefly. If you're just doing a very simple search task, you are less likely to get much in the way of prevalence effects that are anything more than just a motor error. But I don't know that anybody's ever done this, the spider version.
Sounds like a good idea. So there's two questions that I think go in the same direction. They ask about biases. So one is by Natalie Butcher. To what extent might confirmation bias be playing a role? That is, if, for example, a radiologist knows certain occurrences are unlikely, could they be looking for evidence to confirm this assumption that the scan won't have such an anomaly? And I think we can consider this together with Robert Bjork's question about biases in real-world social contexts. So his example is assuming or not assuming that a given person supports compulsory vaccination, given what else we know about that person, such as where they live, who they voted for, and so forth. So do we know anything about these biases taking place in these tasks?
Yeah, I think that the Bjork question points to a fun experiment that I don't think has been done, whether or not your political biases would influence what you would, how you would search under conditions of prevalence. That's interesting. There are efforts to Natalie Butcher's question. There are efforts, excuse me, to try changing people's notion of the base rate. So another way of analyzing all of this is to think of these as versions of base rate effects. And people have tried manipulating that. And I don't know, in a medical setting, I'm not sure that how often a radiologist, let's say, is trying to confirm that something is not present because it's unlike, well, they probably wouldn't verbalize that, but that in some fashion, that is what pushes these criterion effects around. And there certainly are radiology protocols where your job is not to detect the anomaly, but to declare that nothing is present. Oh, that's also true in checked baggage land, in fact. So when you're or in baggage screening in general, in baggage screening, the task isn't really to find the target. The task is to confirm that there is no target present. Because so if you imagine that somebody takes their gun and puts it in a nice lead box so you can't see into the box, and the X-ray of that bag shows up and there's just an unrecognizable black box in there, that's not a target per se that you're detecting, but that's going to require that the bag be opened, because the job of the airport screener is to confirm that there's nothing dangerous here. So we've never actually done that experiment directly of making the instruction confirm that there's nothing here. It might be worth doing sometime.
Mark Zaya Hawley asks, what's next? So any upcoming solutions for the prevalence effect?
Well, I've come to the conclusion that the prevalence effect is actually a long-term employment scheme for a modest set of us in research land, because there are not simple solutions to it, and we keep clever people keep coming up with clever ideas. The group out of J. Pratt's lab in Toronto that is saying, well, pick a target every time, and you're bound to get more of the real targets than you would if you're just quitting certain. That's a good, clever idea. The trick for many of these is to figure out what is the solution that would also work in the real world. So double reading, good solution. definitely cuts down on the error rates. Doubling your workforce, often not a great solution, right? Though the double reading version that might be a good solution is if you have your software that can do that can be one of the readers, right? Because your software, might be expensive, but once you've got it, you've got your second reader. Of course, if you could get your software to just do the task well enough to take the human out of the loop, that would be different, because these criterion shifts are very much a human behavior effect. The software, if it's making a decision, the software needs to have a criterion too, but you, the programmer, can set it. And the fact that it is just saying no, 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 no 1,000 times for every target it finds, that does not disturb your AI system. The problem at this point is that nobody's systems for any of these real world tasks are good enough to operate independently. At this point, they all require some form of human oversight, and the same sort of issues that we've been talking about here still arise when you combine the AI system and the human being. So I hope it's not actually full employment for a small subset of us forever. It would be nice if somebody would come up with the brilliant solution.
Right. And there's some interest in the categorical search study, whether that has been published yet or can be looked up somewhere.
Yes, that is published. What I will do is I will pop the citation in the chat.
Yeah, that'd be great.
If I can actually find it in real time here. But while we're multitasking, you can feel free to queue up another experiment.
Yeah, we'll stick with the category where specific item result. So Anne Bröder is wondering whether there is a model, perhaps a computational model, that would predict this or explains this. So he says, I would suspect that perceptual features of the specific items are well defined, whereas the category perceptual features are not. Hence, a feature match for the former should be much easier. And maybe you could provoke a prototype effect for the category items.
Yeah, if I showed you the full data for that experiment, you would see a certain amount of confirmation for what you're saying there. What seems to be happening in the mixed hybrid case is you've got to decide when to quit. People base their quitting decisions, particularly when the target is, when the specific items are high prevalence, they put their quitting threshold at the amount of time it would take them to determine that that specific mixed drink is not present. As you say, it's harder to identify a member of a broader category. You can see that if you just do the category search by itself. The absent trials in particular now take much longer. And the problem seems to be that what people are doing is they're putting a quitting threshold on the mixed task that works perfectly well for the specific target, but isn't long enough, isn't giving you enough time to go and find or to identify the categorical one. It's not that the categorical targets themselves are hard to identify. They are somewhat harder than a specific item, but it's the distinction between identifying this bunny and any bunny or any animal. They're all basically trivial. It'll take you a little longer to do any animal. And that seems to be a really important piece of what's killing you in this particular task. it's also another one that's quite depressingly immune to your own desires. It seems quite cognitively impenetrable. When I run it on myself, I still make more categorical errors.
And Rachel Hertz is wondering whether it's better to be a naive observer or an expert in terms of having a lower miss rate.
Hi, Rachel. That's a good question. The answer is yes, both. The difficulty, so naive observers will tend to look at stuff that that experts don't look at. So if you think back to the golf ball demo that I did at the beginning of the talk, if you were totally, if you were, you know, from deep space somewhere, you would do better at that task than regular old humans who are at least somewhat experts on where golf balls should be on mini golf courses. Just because your search would be a search for small, white, and round and wouldn't have any of the what we call scene guidance properties in it. And in that case, a naive observer might do better. My own personal example of a naive observer doing better is I got into this whole field because I got a job in high school working at the then Bell Telephone laboratories, where they had an excellent group of people doing vision research. And one of the experiments in John Krauskopf's lab, for those of you who may know him, wasn't working right, and nobody could figure it out. And I, at age 16 or 17, didn't know squat about nothing. And I'm staring at the computer code, and I noticed, you know, hey, here it goes 1, 3, 3, 4. Shouldn't it go 1, 2, 3, 4? I mean, I don't know why, but most of the time in my world, things go 1, 2, 3, 4, not 1, 3, 3, 4. And that was an example of a totally naive observer finding something that that the pros were just not finding because it wasn't a sensible thing to look for. And that sort of effect certainly happens. On the other hand, experts are experts for a reason. If you just point naive observers at mammograms or bags at the airport, there's a lot of stuff that they're going to miss simply because they're not expert enough. At the airport, improvised explosive devices are the great example of this. It's just really hard to do without some sort of expertise. So there is a trade-off there.
Okay, thanks. And then we have an anonymous question, which is about the replication of the PICC results you showed. And so to this viewer, the graphs look way more like one would start to doubt the original finding.
I guess.
I'm wondering if this could be another example of us not questioning surprising findings enough. Maybe we can see that graph again.
Let's see here. Let's share the screen, PowerPoint, share. So what Anonymous is referring to, I think, is that here it was nice and clear that, so the dark blue line in both cases is 50% feedback, and the other line is 10%. Is 10% prevalence, sorry, 50% prevalence and 10% prevalence. And you can see that with feedback, the effect, the curve is shifted to the right, and without feedback, the curve is shifted to the left. And I think what the questioner is pointing out is that in this Bubakiki version of it, that's a mediocre shift to the left. And you will notice that there's a little question mark in my pick arrow there, acknowledging exactly that point. What I would say is that we're on like experiment 20 in the various studies of this particular effect. What is deeply reliable is the difference between feedback and no feedback. So you get a shift here, you get a shift with feedback, and arguably not much of an effect with no feedback. The difference there shows up very reliably. If you were going to want to bet on which effect would be bigger, it would be the classic shift to the right, not the shift to the left. That shift is somewhat less marked under normal circumstances, but there are conditions under which the pick effect is actually more dominant. And that is part of the motivation for this slide, saying that we don't fully understand what's pushing those effects around. Feedback is part of it, but it's a fairly complicated story. And going back to the earlier question of how come you haven't cured it yet, what we're hoping for, one of the reasons for mucking around in this particular complicated space, is that, here at least, hey, I can push the effect to the left or to the right. If I could grab control of that in a useful way, could I put observers' criterion where I wanted it for any given task? That's the goal, but we don't really understand the effect well enough to do that just yet.
Okay. And now Alan Hobbs is wondering about the difference between an automatic search and a controlled search that requires conscious attention. So automatic search when targets pop out versus controlled search requiring conscious attention.
You can get prevalence effects in pop-out searches, but they're smaller and more fragile. And that's basically just a sort of a floor effect problem. Largely, I think there's just not enough. If you're looking for red among green, unless your subject falls asleep, they'll see that red item when it shows up. That becomes almost a vigilance experiment. There are, as I think I put up one of Alan Badley's old references, there are interesting prevalence effects in vigilance studies, but they're less marked, less easily shown than with more complicated tasks.
Okay. And then Jeffrey Toth asked or noted that all of the targets are images, and so he was wondering about alphanumeric search. So searching through a series of multi-field displays wherein all of the fields contain numbers or letters or words. Todd Horowitz has already commented on this about the T versus L search, but wanted to make sure whether there's anything you want to add on alphanumeric search.
There was. So Todd's answer is certainly a right answer in the sense that you certainly get reliable prevalence effects with things like T's and L's. What Jeffrey goes on to say is that the case I'm most interested in is multiple field displays that occur in cybersecurity. And that's also a low probability situation. And I think he's thinking of these situations where you're down in the control room looking at 16 monitors and trying to decide if anybody's shoplifting at your department store out of one of them. I have the feeling that somebody did that. Todd, where are you? You're supposed to be answering this one, if you can remember, or if you happen to be the author of that and you're on this call, pop it in the chat or in the Q&A somewhere. I would, I think that the situation that you're describing, well, if Jeffrey is thinking about the situation where you're monitoring like 12 monitors or something like that, I think there's some work on it that's at the intersection of the vigilance literature and the and this search literature. It doesn't have quite the same trial structure that the search experiments do. So the analysis would be somewhat different. But I'll bet you good money that that the prevalence effect will show up there, right? And you can sort of imagine this for continuous tasks in like video game lands, a video game where nothing happened for 2 hours and then the bad guy popped up or something like that would be a very different video game than the one where somebody's popping up out of every bush trying to do you in.
Right. And then Brad Stillwell is wondering whether prevalence is tied to the context of previous searches or tied to mere exposure, or perhaps both. In other words, does the prevalence effect depend on the location of the object relative to other objects, so contextual cueing, or is the prevalence effect spatially contextually agnostic?
There are certainly, I mean, it would certainly interact with things like contextual cueing. That mini golf example is in a sense an example of that. You're missing the golf balls in part because golf balls just don't show up where I put those golf balls. The basic prevalence effect in the lab is a function of relatively recent history, but prevalence effects, to the extent that they occur in the world, are undoubtedly happening over a much longer, experiential window, right? And under most circumstances, you simply don't do 1,000 trials of the same search, but you will. It's virtually impossible to do the experiment, but I'll bet good money that you will be more likely to miss your search for something that is rare in your environment than for something that is common, even though you haven't done 500 searches for the rare thing in the last 5 minutes or something like that.
And we have two questions here that wonder about training. So Robert Bjork says, what do you think the potential for training might be? Phil Kelman at UCLA, for example, has shown that people can be trained to be significantly better at reading EKGs. And Susanna Lorenzo also asks whether you think previous intensive training of radiologists with unusual targets could help to avoid the low prevalence effect through a recollection. So she suggests through a recollection mechanism that would help to detect those low prevalent items in future occasions.
Yeah, I think in the answer to both of those is yes, training is going to make a difference, and it's going to make a difference. And in most expert domains, even if they don't necessarily know specifically about prevalence effects, the practice in the field is in part designed to counteract a variety of these things that we study in the lab. So a lot of radiology tasks involve basically checklist routines, either actual on-screen checklist, or you sat next to your mentor and she taught you that the way we do abdominal CT is we look here, we look here, we look here, we look here. And these sorts of things are training that will, at least in part, counteract the tendency to miss low probability events, because you're going to force yourself to a fixed scan path of some variety. Doesn't seem to immunize you. The experiments that we have done with experts of various sorts tend to show the basic prevalence effects. But what you do is what I think they're mostly doing is trying to put in safety measures. A little like what we were trying to do unsuccessfully with the speed limit experiments. We thought that a perfectly good technique that didn't work in our case for avoiding these errors is to just keep people on the image long enough to find what they should be looking for. So I think most of the prevalence effects, or most of the efforts to avoid prevalence effects, basically involve putting in some sort of scaffolding to insulate you.
Mm-hmm. And so maybe related to training, but a different approach. So not training the people doing the search, but rather, so Lisa Blalock suggests that maybe automation could help, in the sense that you use something that that clears negatives and so increases the prevalence. So her specific suggestion is that in cytology, they use ThinPrep to eliminate clear negative. Yeah,
this is very much I think the wave of the future for AI in a number of medical imaging settings, which is not so much to use the AI to say, oh, look, here's the cancer or whatever right here. That what the AI is used for is to say, there's just nothing here, right? You just don't need to look at this. Now, the difficulty with that is if the system was good enough to know that perfectly, then you're home free, of course. But in fact, all the AIs have an ROC curve like you do, and just about in many tasks, just about as good as an expert. But that's nothing like perfect. So now what you've got to do is you've got to put your criterion at some operating point. What percentage of the cases are you willing to throw out? And the answer so far in most of the settings that I know is that you can possibly throw out a third to a half of the cases as, I am willing to let my machine throw this out, even though the probability that there's anything in the remaining half of the cases is still very low. I can throw out these half because I'm really sure I'm not getting sued over that. You've got to be really conservative about that. And so for the specific improvement that Lisa's looking for, the problem is you'd need to be able to throw out lots more in these low prevalence screening situations, right? If you throw out half the cases in mammo in a typical screening population, you've gone from 3 cases in 1,000 the radiologist is looking at to 6 in 1,000. You're still at a terrifically low prevalence. But what you have done is you've cut the workload in half, and that's a great thing. And if you could really reliably cut the workload in half, well, gee, then maybe you can double read everything, have 2 humans look at it, and that's going to help. So it's the direction that Lisa's pointing in is definitely a useful direction that various AI applications are working on. It's 1 o'clock.
Yes, it
We
is.
should probably call it a day.
Yes, I was just going to suggest that. So looking at the time.
Lewandowski left hours ago.
Thank you so much also for answering all these questions. We still have a few open. Maybe if you look at them, maybe some you can put a link up or something.
Yes,
yeah,
certainly if anybody has ongoing questions, just pop me a regular old-fashioned email and I'm happy to.
Yeah, maybe if you want to leave your email in the chat.
Oh, there's a thought.
So thank you too much, and thanks to everyone also for the great Q&A. I'm not sure if the Psychonomic Society wants to say final words. Or if not, I can announce that the next One World Cognitive Psychology Seminar will be on October 20th with Julia Strand on Beware the Jingle and the Jangle, Cautionary Tales from Research on Listening Effort. So we hope we see you again in about a month. Bye.